You've seen the checklist. It's posted on every survival forum, duplicated in every emergency manual, and preached by every backyard guru. Stockpile 1 gallon of water per person per day. Go to the store, buy the heavy-duty blue food-grade drums, clean them, fill them straight from the garden hose, seal the bung caps tight, and stash them in the dark corners of your basement or garage. Then, you sleep soundly at night, completely convinced that you have secured the absolute baseline of human survival. It is a deeply comforting narrative. It is also an engineering delusion. Water is not a static commodity that you can just lock away in a container like gold bullion or canned rations and expect it to remain unchanged. Water is the universal solvent. It is a highly reactive, dynamic fluid that actively, continuously interacts with its container, its surrounding environment, and microorganic life on a molecular level every single second it sits there. While you are busy counting your stored gallons and checking off boxes on your prepper spreadsheet, a silent countdown timer is ticking away in the dark. Hidden fluid dynamics, continuous hydrostatic pressure, chemical breakdown, and anaerobic biological colonization are quietly, systematically converting your pristine emergency reservoir into a toxic chemical and biological trap. Today, we're looking past the superficial, sensationalized survival guides. We are putting away the folklore and looking directly at the raw physics of long-term fluid stagnation. Welcome to Protocol Owl. Let us dissect the cold empirical data. Let us begin by addressing the container itself. The overwhelming gold standard choice across the entire survival community is high-density polyethylene, specifically designated as HDPE number 2. It is widely marketed as chemically inert, highly durable, and completely food-safe. Under short-term laboratory conditions, this assessment is entirely accurate. But survival timelines are not short-term laboratory tests, and your storage environment is rarely a controlled, temperature-regulated laboratory. When you fill a standard 55-gallon drum with water, you aren't just storing a liquid, you are creating a highly localized zone of continuous, unyielding hydrostatic pressure. Water is heavy. It weighs approximately 8.34 pounds per gallon. Inside that drum, the fluid at the bottom exerts a constant, relentless physical force against the clastic walls, roughly 0.43 pounds per square inch for every single foot of depth. Over months to years or 5 years, this constant mechanical stress triggers a well-documented material science phenomenon known as polymer creep. Polymer creep is the tendency of a solid material to move slowly or deform permanently under the continuous mechanical stress of long-term loads. As the high-density polyethylene chains are subjected to this constant outward hydrostatic pressure, their tightly packed crystalline molecular structure slowly begins to untangle and deform at a microscopic scale. This mechanical deformation directly accelerates a destructive process called chemical leaching. You must understand that even food-grade plastics are not purely organic, pristine barriers. During the industrial manufacturing process, various chemical catalysts, antioxidants, slipping agents, and ultraviolet stabilizers are mixed into the plastic resin to help mold the shape and prevent the drum from cracking on store shelves. When the container is subjected to continuous hydrostatic load, combined with the inevitable subtle shifts in seasonal ambient temperatures, these embedded chemical compounds begin to break free from the deforming polymer chains. They slowly migrate outward, dissolving directly into your stagnant water supply. Worse still is the completely ignored reality of polymer porosity. At a macroscopic level, a blue plastic drum looks completely solid. At a microscopic engineering level, plastics are semi-permeable membranes. They possess a measurable gas transmission rate. If you store your water drums directly on a bare concrete garage floor or in a shed right next to gasoline canisters, lawn fertilizers, chemical cleaners, or vehicle exhaust fumes, a silent, multi-year cross-contamination occurs. Volatile organic compounds from those ambient air hazards can and will slowly migrate directly through the semi-permeable HDPE walls over an extended period. Because water is a universal solvent, it eagerly pulls these airborne chemical vapors straight through the plastic and dissolves them into your drinking supply. You will not see it happen. You will not smell it when you open the cap initially, but the chemical profile of your critical life-saving asset has been permanently, irreversibly compromised before you ever take a single sip. But chemical leaching is merely the foundational flaw of static storage. The far more aggressive, immediate peril waiting for you in the dark is biological. A massive percentage of the survival community operates under the dangerous assumption that if they simply treat their water with a splash of standard household bleach or chlorine during the initial storage process, that water will remain completely sterile and safe indefinitely. This represents a profound, potentially fatal misunderstanding of basic biochemical half-lives and chemical volatility. The active ingredient in household bleach is sodium hypochlorite. It functions as a powerful sanitizer by actively oxidizing organic matter. The crucial engineering detail here is that the very process of sterilization consumes the chemical itself. Furthermore, free chlorine is fundamentally unstable and highly volatile. Even in a perfectly sealed, pitch-black container, free chlorine molecules naturally dissociate over time, breaking down into completely inactive chloride ions. In a standard stagnant system, the half-life of residual free chlorine is shockingly short. Depending on the ambient temperature and the initial organic load of the water, your active sanitizer levels will naturally decay to absolute zero within 6 to 12 months. Once your residual chlorine level falls below the critical threshold of 0.2 milligrams per liter, your massive water supply is officially entirely defenseless. It's a wide-open, unmonitored ecosystem waiting for an invader. Now consider the exact environment inside that dark, stagnant container once the chemical sanitizer has died off. It's completely still, totally dark, and entirely devoid of dissolved oxygen. These are the absolute peak, flawless operational parameters required for the rapid colonization of anaerobic bacteria. No matter how clean you think your initial water source was, microscopic bacterial spores, wild yeasts, and specialized environmental pathogens will inevitably enter the system. They enter through microscopic gaps in the bung cap threads, through flexible plastic lines of your transfer siphons, or directly from the ambient air the very moment you crack the seal to inspect it. Without active fluid circulation or dissolved oxygen, standard aerobic organisms die off, but specialized anaerobic organisms thrive. They settle onto the interior surfaces of your container and begin to construct what microbiologists call a biofilm. A biofilm is a highly complex, defensive extracellular matrix made of polymeric substances that firmly glues the bacterial colony to the plastic walls. This biofilm acts as an incredibly robust physical shield. It completely protects the reproducing bacteria underneath from any late-stage chemical surface treatments you might try to pour into the tank later. As these anaerobic colonies metabolize the trace minerals and remaining organic matter inside the dark tank, they produce and release highly toxic metabolic byproducts. They generate hydrogen sulfide gas, which smells of rotting eggs, iron oxides, and highly dangerous bacterial endotoxins. When a true crisis hits years down the line and you finally open that barrel out of desperation, the water might look perfectly clear to the naked eye, but its microbiological profile is deeply hostile to human physiology. Drinking that stagnant anaerobic fluid directly will induce acute gastroenteritis, severe bacterial dysentery, rapid vomiting, and profound systemic infection. In a severe grid-down scenario where medical infrastructure is non-existent, consuming this water will cause rapid, catastrophic dehydration, the exact identical condition you were trying to prevent by storing the water in the first place. You have effectively spent years hoarding a hidden physical liability underneath a blue plastic lid. We do not analyze these structural engineering flaws merely to induce despair. We analyze them so we can apply clinical logic and engineer definitive, data-driven solutions. If you want to survive the reality of long-term hydro-peril, you must completely alter your mental model. You must stop treating water like a static, dry good. You must begin treating it as a living, dynamic fluid system that requires active management. First, we must completely eliminate the mechanical and material vulnerabilities of containment. If long-term static storage is your only operational option, you need to look past standard consumer-grade plastics for your primary reserve. High-grade, food-safe 31-6 stainless steel or specialized heavy-duty fiberglass tanks with certified food-safe epoxy linings offer drastically superior structural resistance to polymer creep, zero gas permeability, and absolute protection from chemical leaching. Furthermore, you must completely break the environmental migration pathway. Never, under any circumstances, place any water storage container directly on bare concrete. Concrete is highly porous and holds moisture and chemical residues.
Always elevate your storage vessels off the ground using heavy-duty wooden or composite pallets. This simple mechanical separation creates a crucial air gap that stops the thermal and chemical transmission from the floor dead in its tracks. Second, you must institute a strict, non-negotiable protocol for fluid rotation and mechanical aeration. Stagnation is the ultimate ally of the pathogen, therefore kinetic movement is your primary defense. Number 1. Active cycling. You must commit to a minimum 25% volume rotation of your stored water every 6 months. This regular displacement flushes out aged fluid and allows you to introduce a fresh, controlled dose of residual sanitizer to keep the ecosystem suppressed. Number 2. Mechanical aeration. Prior to anyone consuming water that has sat stagnant, that fluid must be aggressively agitated, shaken, or passed through a multi-tiered aeration cascade. By violently introducing atmospheric oxygen back into the fluid, you fundamentally destabilize, suffocate, and kill the strict anaerobic bacteria that flourished in the deep oxygen-deprived dark of your tanks. Number 3. Point-of-use UVC and ultrafiltration. Do not make the mistake of relying on simple, low-pressure gravity charcoal filters to clean a compromised tank. Biofilms will bypass them. A true clinical survival protocol requires a rigorous multi-stage filtration architecture. The fluid must first pass through a submicron sediment block to physically trap and remove the fragmented biofilm sheets and suspended particulates. Next, it must flow through a high-density activated carbon block to absorb leached volatile organic compounds. Finally, the fluid must pass directly through an inline UVC sterilization chamber. This high-intensity ultraviolet light disrupts the core DNA of any surviving anaerobic pathogens at a molecular level, rendering them completely sterile and harmless. The ultimate engineering solution to the water crisis, however, is not to store massive static oceans in your basement and hope for the best. The ultimate strategic goal is source mastery. True tactical security means establishing redundant, passive purification systems that harvest dynamic, moving water directly from your surrounding environment. True safety lies in engineered systems that rely on constant kinetic flow, solar distillation, and deep earth geological filtration rather than relying on a static, decomposing plastic box. Survival is never a measure of how much material you can mindlessly hoard in a corner. It is an exact measure of how accurately you understand the immutable physical and chemical laws governing those materials over time. 1,000 gallons of stagnant, contaminated water is not a survival asset. It is a biological hazard. Look closely at your emergency infrastructure. Audit your structural assumptions. Ground your entire operational strategy in hard chemistry, material science, and fluid dynamics, rather than relying on comfortable, unverified prepper folklore. Fantasy will fail you when the grid drops. Only data will keep you standing. Protocol observed. Knowledge retained.